We're on.
We're on. Okay. Find the integral of x plus cos 2x squared. I think, am I right in thinking that your instinct of how to start this would be to do what?
Panic.
Cry. No, that wasn't the right answer.
Bad hands.
Multiply it out. That's the instinct. And it's right to go with that instinct, to multiply it out to start with and see what we get. So, when we multiply it out, we're going to get x squared plus x cos 2x plus another x cos 2x, so plus 2x cos 2x plus cos squared 2x dx. We've multiplied it out, and it's got a lot worse. But we're now going to actually pull this apart and do it as separate things, because we've really got three separate integrals, haven't we? We've got an integral there of x squared, we've got an integral of 2x cos 2x, and we've got an integral of cos squared 2x. And we can deal with each one of these separately, and then put them back together at the end. So let's do that. Let's start with the one that I've shaded in blue there. The integral of x squared dx. Well, that's okay. That is x cubed over 3. I'm not sure about my plus c. I'm going to put plus c in at the end. I'm not going to forget. I'm just going to remember that at the end, once I've done all these integrals, I'm going to have one constant. So it's not forgotten, it's just we won't put it in every stage. Okay, if we look at the yellow bit. The yellow bit was the integral of 2x cos 2x. Okay. What type of integral is this? It's by parts, isn't it? It's product. And the two things are not directly related. One isn't the derivative of the other. 2x isn't the derivative of cos 2x, and it's not the derivative of 2x. So we haven't got that link of substitution. We're going to do integration by parts. When we do integration by parts, we're thinking of one thing that will get nicer when we differentiate it, and another thing that won't get too much worse when we integrate it. So which way around is it here? Which bit's going to get nicer when we differentiate it? The 2x. And the cos 2x isn't going to get any worse. It's just going to go to a sign-related type thing. So we're going to say that the differentiating bit is 2x, and the integrating bit is the cos 2x. And if we differentiate 2x, we get 2. And if we integrate cos 2x, we get a half sine 2x. Oh, hang on. Does it go negative? Sim card, sine integrates to minus cos, ard. But I got that on video. But this one doesn't, so we're right. We're okay so far. What we're doing, oh yeah, we're putting it all together to give us u times v. So, well hang on, that's nice, isn't it? U times v, the 2.5 cancel out, so we've got x sine 2x minus the integral of v du by dx. And again, the 2 and the half cancel out. Yeah, that's good. So we're there. So this second part, the yellow bit that we coloured in the first integral, we're now ready to finish off. If we integrate sine 2x, we get
minus a half cos 2x.
Minus a half cos 2x. How do you remember it was minus a half?
Sim card.
Sim card. And of course it's plus there because it's minus minus. Brilliant, this is going so well. Again, we've got plus c in there, but you know, I'm not. Should we write them in? We should write them in, shouldn't we? So we don't forget. Okay. We'll put it there. Just so it's there. Right, the green bit was cos squared 2x. Okay? And we've just talked about this. This is the trig identities thing. Our way of integrating sine squared, cos squared, tan squared
Degeneration.
is to use the trig identities. If in doubt, we could always derive them again. We remember that, we'll remember this one, don't we? Cos 2a is cos squared a minus sine squared a. And we want to find cos squared, so we've got to get rid of the cos squared, so that's 2 cos squared a minus 1. So if we rearrange it, we get cos squared a is a half 1 plus cos 2a. We may have learned that, but if in doubt, we could always just find it out again. Now here, we've got a is 2x. So this integral becomes, instead of cos squared 2x, it's half 1 plus cos 4x. 4x okay? A is represented by 2x, so we've got twice 2x, so 4x. Fit there. And we can integrate this. If we integrate this, we'd get a half of 1 when we integrate it is x, and cos 4x when we integrate it, we'll go to a quarter sine 4x. So we've got an eighth of sine 4x. So I'll get there. We've done 3 integrals now, and so we're ready to put them all together. So, the integral of x plus cos 2x all squared equals, and we had it as 3 parts, so the first part gave us an answer of x cubed over 3. The second bit of it gave an answer of x sine 2x plus a half cos 2x. And the third bit of it gave us an answer of a half x plus an eighth sine 4x. And we're remembering that we're combining all of these little constants that we had into one big constant at the end. And we're going to leave it like that. There's not an awful lot we can do with that. We can't really combine anything there. We could maybe factorise the sine 2x bit, but it's fine as it is. That was the 9 marks, which is quite good. And the question goes on to this. The diagram shows part of the curve y equals x cos 2x from 0 to pi by 2. The shaded region bounded by the curve, the axes and the line x equals pi by 2 have rotated completely about the x-axis to form a solid with revolution of volume v. Find v, giving your answer in an exact form. Well, this has got to be linked in. Now remember, we've used the word synoptic. We've said that core 4 is entitled to draw on anything from any of the other core modules, and so volumes of revolution is C3. But all that they're actually wanting out of the volumes of revolution stuff here is you knowing that in order to calculate that volume is the integral. Remember, it's the integral of pi y squared dx between 0 and pi by 2. It's core 3. Volumes of revolution is core 3. And y squared is what you get if you square that. So this is, remember, this depends on who taught you this, but remember you can take the pi in front of the integral sign.
Yeah.
So this is pi times the integral from 0 to pi by 2 of y squared, x plus 2x squared dx. Well, hang on. Where have we seen that before? That was part 1. That was what we just integrated. And so we know the answer to that. We know that that is pi times, and it was a bit of a mess, and I'm lost exactly a note again. What was it? 1/3 this might not be the order that we have it exactly. We have 1/3 x cubed plus x sine 2x plus a half cos 2x plus a half x plus an eighth sine 4x. I'm running out of space between 0 and pi by 2. Of course, we had plus c on the end of our answer, but we're not writing that now because we're between limits and you don't put plus c in when you're integrating between limits. It's nasty, isn't it? Because had you not got a sensible answer for part 1, then the question stopped here. You know, there was nothing that you could do with that because you didn't know what it was if you hadn't done part 1. So these 13 marks for this last question were all lumped in together.
Did you not get method marks if you just used your part 1 answer?
Well, you would, but there were only 4 marks. You get a method mark for this, for saying that that's what the integral was. You get a method mark for using the limits correctly or whatever you had in here. But that's it. That's as much method marks as you're going to get. So you get 2 out of 4, but that's all. We need to put the limits in, and this is going to be horrible. This is going to be pi times, well, okay, let's do it. 1/3 of pi over 2 cubed. That's going to leave us with pi cubed over 24. No. Yes? We've then got pi over 2 times sine of pi. Oh, but sine of pi is 0, isn't it? So that's 0, that next term. We've then got a half times cos of twice pi over 2. So a half times cos of pi. Cos of pi is -1, so we've got minus a half in there. We've then got half of x, pi by 4. We've then got 1/8 of sine 4 pi over 2. 4 times pi over 2 is 2 pi. Sine of 2 pi is 0 as well. So that's 0. That's the first bit. Let's squeeze a bracket in there. We're then subtracting what we get when we put 0 into that, which would be 1/3 of 0. 0 times sine 0, so that's 0 as well. Cos of 0 is 1. So we've got a half coming out of that bit. That's 0 as well. And sine of 0 is 0. So I'm putting the zeros in just to remind you that I've actually dealt with those terms. Altogether, we've got pi times pi cubed over 24. I'm happy about that term. What else have we got? We've got pi by 4. And we've got minus a half minus another half. So I think we've got -1 in there. If I want to, I could multiply out the factor of pi. Thanks. But that's it. There's my answer. I'll underline it. There we go. Great.